Today we'll be talking about two very important parts of wastewater management. One is used water management we'll be talking about. We have three experts lying with us who will be speaking about, and then in the later part of the session, we'll be speaking about co-treatment at the sewage treatment plants. So for used water management, we have Mr. Venkat, who is a civil engineer, and it is Masters in Environmental Engineering from IIT Kanpur back in 1983. All through, he has been involved in the design of water, sewage, and wastewater treatment plants. Presently, he is working on an overall water management, which includes recycling, reuse of treated water or used water. And he has worked for several industries and government establishments. Later, we have Mr. Gangadhar Reddy. Gangadhar Reddy or Danti Reddy, commonly known as, or very colloquially known as Ganges Reddy, is an environmental sustainability expert, and he is the CEO and co-founder of Blue Drop Enviro Private Limited. A mechanical engineer by qualification, he has spent 22 years in the USA, but after coming back to India, out of his passion for the environment and believing in the best practice for eco-friendly human existence, he chose to get into wastewater treatment, bringing innovation and sustainability into the game of water treatment. We also have Mr. Srikar. He's the director of Revolve Engineers Private Limited. He's a postgraduate engineer from New York University in the field of wastewater resources engineering. Now he's heading over 80 plus freshwater, sewage and effluent recovery and recycling projects. He works with his team of young engineers and graduates providing end-to-end water and wastewater distribution, treatment and reuse solutions. He is supported by stakeholders from the MEP industry for the past 5 years in various aspects of plumbing also. And in the later part of our session today, we have Mr. Dorai Narayana, who is a civil engineer. His professional experience spans over 40 years in the sanitation and sewerage industries and has worked for consultants, governments, as well as India Water Consortium and the Malaysia National Sewerage Utility Company. He has also contributed in advisory capacities for various sanitation and sewerage projects in several developing countries in Asia and South Africa. Since 2015, he is a freelance consultant supporting sanitation and sewerage projects in Asia, Africa, and is a consultant to the Bill and Melinda Gates Foundation. Has many papers and publications to his credit, with a notable book from IWA on co-treatment of fecal sludge. And today we'll be listening from him elaborately about co-treatment of fecal sludge. With the introduction of these speakers, I would now request Professor Chari to take on the conversation further with used water management. And thank you, sir. Thank you so much.
Thank you, friends, for joining. Pleasure to meet all of you again. As I said, I look forward to these interactions, and thank you very much for joining. So today we'll be looking at a very important component of the citywide inclusive sanitation. So far, our focus of attention was on fecal sludge septage, as we say, from on-site systems, which is basically dealing with the night soil. Basically, क्या करते हैं? We use septic tanks, on-site systems, basically to deal with the night soil. We flush, it goes into a septic tank, then we keep it there, contain it, and then we evacuate it through a suction system and then take it to fecal sludge treatment plant. So that's one part of this story. But as we know, every household, for night soil cleaning and other activities, we may use about 10 liters of water per capita. But on an average, a citizen is using 130 plus liters per capita per day. So where is that 120 plus liters of water is going? Some is going for drinking, but bulk of it is coming as used water. It's used for, number one, for washings, for cleaning, for kitchen activity, for bathing, and we call this as sullage or grey water in a common language. Now, sullage and grey water is in large volumes. Septage is in small volumes in a concentrated way, but sullage or grey water is in large volumes. It may not be as concentrated as septage, but if I look at the volumes and the load, it's phenomenal pollution. And on top of it, the overflow of septic tank also is joining the sullage. So given this situation, though we may have on-site systems, though the countries have the regions in this, the urban areas in this region, maybe 80%, 90% dependent on on-site systems. And septage management is important. But we cannot ignore grey water management from environmental protection and from public health point of view. We can prioritize, like risk prioritization. We prioritize septage management, but from a larger impact and public health and environmental impact, we need to deal with this grey water management, or often called as sullage. So today's conversation from an overall urban improvement, while on-site sanitation, septage management, which we have been discussing, is super important. But this is equally important because of the large volumes and the potential it can cause. So today what we have done is, it is important for us to think about how to plan. So Mr. Venkat is the authority in this subject. He's been advising states, cities, international consultant. He will tell us about how to plan and what are the broad solutions available. How do we choose a solution? Then followed by two interesting innovative solutions. One is nature-based solution. And then Mr. Srikar will be speaking about package treatment plant, often called JOCASO. If you have a building, if you have a house, if you have a multi-story gated community, you can treat the waste where it falls. That's the most effective way. So these are the three different presentations, and there will be a lot of questions which I have prepared myself for this question, because all the three are authorities in this. So I have to prepare myself to ask questions. So without taking much time, I now request Mr. Venkat. He's going to share the deck later. The font size are a little less. Don't worry about it. We will share with you the complete presentation with all the details as we after the session. But I think he has a lot of wisdom. So over to you, Mr. Venkat.
Good afternoon, everyone. Hello, friends. Basically, what I would like to start my presentation is by saying that water is a very limited resource. The net water availability, as we see in the days to come, is reducing drastically. It is said that if water availability is about 2,000 cubic meter per person per annum, then we are in a water safe province. Unfortunately, most of us are coming into water scarce and severe water scarce provinces. And more importantly, whatever good resources we have, we are converting those good resources into unusable resources because of pollution. Like there are 400 lakes in the city I stay, that is Hyderabad, and none of the lakes are fit for drinking purposes because all the lakes receive a lot of grey water and black water. So it is very important that we stop this pollution and we work out ways and means of what you call treating this water and reusing it. Fundamentally, we cannot call used water as wastewater. It is also to be considered as a resource. Unless until we increase the efficiency of water with this increasing population and the water demand, we cannot meet the two ends. So it is very, very important that we treat the used water and reuse it, and preferably depending on the situation that we will discuss in the future course of the presentation, as to doing it in a decentralized manner or a centralized manner. Next slide, please. Jyotsna? Right. Now, as Professor Chari was saying, we use water for different purposes in the house, and the worst part, or the most highly pathogenic content water and the water with maximum BOD will be coming from the WCs. The rest of the water is coming from various other sources like our wash basins, from our laundry, from our kitchen, and in Indian context, from a lot of floor cleaning and other related activities. Now, to characterize this water is very, very difficult, because characteristics of gray or black or used water is a function of the quantum of water supply and the social lifestyle that people adopt. So if you look at this slide, you will find that the range of the parameters is almost 10 to 15 times. So it is all a function of various aspects, especially the quantity of water supply and the social lifestyle. Next slide, please. Now, in used water quality, the basic parameters of concern. Now, used water, I will use the word used water both for gray water and combination of gray and black water also. Anyway, irrespective of that, the used water will contain solids. It will contain issues related to dissolved oxygen. It will contain nutrients, which are also very important from the viewpoint of eutrophication and other aspects into the final receiving body. It will contain microbial contamination. It will contain inorganic substances, which are very important again from the viewpoint of reuse, recycle, because the inorganics cannot be removed in the process of treatment, which we conventionally follow. And there are other constituents like pH, temperature, odor, color. Not too much of a difference in these things when we talk about domestic wastewater. Next, please. So broadly, if I look into the used water characteristics, I've summed it up in this table. And as I said, the variation is quite large. Even in a city like Hyderabad, where we have a population of more than 1 crore of people, and in different areas, when I go to, I collected samples from different areas to check the quality of the sewage that is generated. And it is quite alarming. Meaning to say, in some areas, the sewage doesn't have an organic load of more than BOD, more than about 50 to 60 milligrams per liter. And in some areas, it goes as high as even 600 to 700 milligrams per liter. And that is all a function of the population of that area and the quantum of water supply and the social lifestyle that they're adopting. Next slide, please. Now, what do we do with the used water? I have briefed it into two pertinent goals. One, the first goal, as far as I feel, is, as I said, used water is a resource. It is not a wastewater. We should look into the reuse potential. Wherever we can have decentralized facilities, we can use treated used water for the purposes like toilet flushing, gardening, vehicle washing, groundwater recharge, or even cooling tower makeup. In the community I stay, we use the treated used water entirely for the purpose of gardening and to a certain extent groundwater recharge. In a centralized treatment facility, the used water can be used for cooling towers makeup, especially if there is a major thermal power station or something of that sort. It can be used for industrial purposes. It can be used for avenue plantation, irrigation, construction, well, not too much about it. And basically some aspects of groundwater recharge and recreation can also be looked into. Then if I have to discharge this water, the issue is I have to meet the regulatory norms. Today in India, the regulatory norms are very stringent. As per the new NGT guidelines, the BOD should be less than 10, the COD should be, this is all for metropolitan and class 1 cities. The suspended solids less than 20, total phosphorus less than 1, total nitrogen less than 10, and total coliform is desirable to be less than 230 per 100 ml. Next, please. Now, there are no standards per se for defining that this water can be reused if it has this quality or that quality. I have collected some information from different sources. And ultimately, when you talk about used water for reuse, the paramount aspects are aesthetics. The water should not have any smell. It should not have any color. It should not have any odor. Added to that, it should not contain any pathogens. And also it should not contain any inorganics, which would finally result into scaling and other related aspects. So these, when this is too small for people to see on the screen, I requested Professor Chari that if we share these things, then it will be more clear to the people. So by and large, if I look at it, mainly the used water after treatment can be reused for at a bulk scale in the industry, in the cooling towers at power plants, for groundwater recharge, to certain extent for recreational purposes, And at the smaller facilities, it can be given back to the township for the purpose of toilet flushing, for gardening and other related aspects. However, there's that stigma always attached that, oh, there's used water, I don't want to touch it, I don't want to reuse it, despite the quality of the water. I have asked several people, would you drink used water if I treat it to levels better than the drinking water you are getting? And I always got the answer most of the times as no. But then when I tell them that this used water is going into a river, and downstream of the river, the population there is using this as their raw water, and that is being supplied for the drinking purposes, then they are a bit aghast, because people just think that you open the tap, you're getting water, you flush the toilet, the water is going away. From where the water is coming and where the water is going is of little concern to most of the people. Anyway, next slide, please. This is a continuation of the quality of the water. And I was just seeing the new guidelines as provided by the NGT, that is the National Green Tribunal. And if I look at the parameters and characteristics that have been specified for reuse applications, I find that the NGT standards are as stringent or even more stringent in some cases than most of the reuse potentials. So in our country, if we follow what the NGT is saying, then by and large, most of the water, barring the inorganic substances, meaning to say in Hyderabad a few years ago, we used to get groundwater. And in groundwater, the TDS, the hardness and other things were so high that reuse of that water for purposes like cooling or any other application wherein scaling is a possibility would have been very, very difficult. Next slide, please. Now, this is a small example I had sketched during one of my projects. Now, normally in most of the cities, we have these rainwater or stormwater drains, which are being used for conveyance of the sewage. So there are houses near to that stormwater drain, and most of the houses let out their wastewater into these drains. Next. So what happens is these drains, they become perennial drains. They carry wastewater not only during monsoon, but all through the 365 days of the year. And unfortunately, they're carrying wastewater. Now, this wastewater, because the drains are not properly lined and they're not seepage proof, this dirty water seeps through the ground and invariably meets the groundwater table. And in the process, the hand pumps and other sources of groundwater which are there in that near vicinity, they are all contaminated. And more importantly, the contamination is because of microbial contamination, resulting into many diseases. As a matter of fact, one of the study I was looking through a few years back said that more than 80% of the hospital beds are occupied because of waterborne diseases, like, cholera, typhoid, amoebiasis, and other related things. And the cost in terms of man days lost and the treatment cost is so high that it has a very good payback period if we avoid this dirty water in the drains and provide clean drinking water to the citizens. Next slide, please. So what was thought is have small decentralized treatment facilities along the drain, and you put in the treated water into the drain and don't let the untreated water or the raw wastewater, gray or black water, be allowed to go into the drain by having some interceptions. After every certain distance based on the situation and circumstances, we again have a small treatment plant, and only the treated water is put back, and that quantity of treated water is put back which is over and above what can be reused and recycled within that nearby areas. So the stormwater would definitely carry only clean water all through the 365 days of the year, apart from rainwater during monsoon. Next, please. Now, where to build the treatment plants, especially in urban areas, we have a lot of problems related to space. So there were different thought processes that came in. We can build the STPs underground, like, some public place, and there you can make it underground and recover it with some plantation and other things so that it doesn't spoil the aesthetics. Most of the drains are quite wide, and there is a possibility of constructing small STPs on top of the drain itself. And if there is land available in a place like Kanpur under the Ganga Action Plan, it was also thought to buy away some of the area where houses are there and construct sewage treatment plants there. Pay for it. It's still worth it. Next, please. The idea ultimately is the stormwater drains should carry clean water or treated used water all through the 365 days of the year. And this water can also be accumulated in some artificial water body, or if there's a natural water body around there, and that can recharge the groundwater. And this water can also be pumped back to places like railway stations for washing of the coaches, the tracks and the platforms. It can be sent back to the industry. It can be sent back to the power plants, because from a centralized facility to recycle back the water for toilet flushing and gardening at individual houses is not a practical approach at all. So we have to look into these aspects where what type of reuse concept can be adopted. And if we are putting in treated used water back into the river, the river ecology and the river cleanliness is also maintained, and downstream users are also happy in the process. Next, please. So these are the reuse potential is at power plants, railway coach washing, industry, and horticulture, irrigation, etc., etc. Next. So ultimately, carrying out decentralized treatment or centralized treatment will result into clean and aesthetic environment all around, and health and other related aspects are, there's a lot of improvement, and overall hygiene is better. So like Professor Chari was saying, the major chunk of the pollution that is being carried out, that is conveyed with the used water, should be avoided, and that can be avoided by providing adequate treatment. Next. Next. This you can leave it. Means this is just a representation of after utilizing whatever is the water that has been treated, the excess is left off into the river by some controlled outfall. Next. Now, how do we select a particular technology or a particular operation for used water? Now, there are various parameters that one needs to look into. First and foremost thing, or rather, I can't say that this is important and that is not important. All have an equal bearing. The quality of the water, the quantity of the water, the location where the treatment plant has to be established, that is availability of land, what is the capital cost, what is the recurring cost, what is the level of expertise that is required to operate one of these such plants, and the reliability of the technology that we are adopting, and so on and so forth. So there are various parameters that we need to look into. Next, please. Now, in the treatment technology that is adopted, by and large, some fundamental unit operations are a must. Among those fundamental unit operations are, we need to have a core screen, a collection well, from where we pump it further into a fine screen and a grit chamber. Up to this part, it is virtually common, whether it is used water, grey water, or combined wastewater, because these are the constituents which are generally found in most of the used water systems, and they go undeterred through the treatment plant. And apart from going undeterred, they create a lot of problems like choking of the pumps. Then the grit will settle down in one of the treatment systems, creating a lot of dead volume, so on and so forth. Next, after this preliminary treatment is over, if you have a dilute strength used water, dilute strength meaning to say somewhere around the BOD is not more than 80 to 90 or 100 at best, you can go for straight away physico-chemical treatment, which comprises of coagulation, flocculation, settling, followed by gravity filtration and adsorption, and finally disinfection. And then obviously the sludge management, we will be generating sludge in the whole process. Sludge management is common in almost all the treatment facilities. I doubt if there's any treatment facility where sludge generation won't be there. Maybe less or more, but end of the day, sludge will be there, and sludge has to be treated. Now, how do we treat the sludge is a question mark, meaning to say it depends whether it is physico-chemical sludge or organic sludge. If it is organic sludge, we can then convert it into manure by going for vermicompost, or we can ultimately, if it is a primary sludge, we can think of getting biogas generation from it. If it is a secondary sludge, we just dry it and use it as a soil conditioner, many cases. And it depends. It depends. Next, please. Now, used water treatment. Fundamentally, we are talking mainly about used water, not for throwing away the water. Throwing away the water means to finally discharge into one of the receiving bodies. The first objective, as I feel, is used water should be treated in such a manner that we can reuse and recycle the water. To reuse and recycle the water, as I said, aesthetics are the most important thing. It should be color-free, odor-free, and it should be pleasant to, pleasant means it should not be unpleasant to look at, and it should not have harmful components. When I say harmful components, am I running out of time, Professor Chari?
Not yet, sir.
You have
Okay.
Another 5 minutes so that we can.
Okay, fine. And I have no issue. Means if I'm running out of time, please sound an alarm.
Yeah.
Right. So the basic idea is to see that we treat the water to such a degree or such an extent that we can reuse it. Now, there are cases, we had this particular project in Hyderabad, wherein there is a nala known as the Kukatpalli Nala, which carries huge amount of wastewater. And it was thought of treating the concerned minister and other people wanted that nala to look beautiful. And then it was thought that only treated water should flow into the nala, and it was to be given on a PPP model. Now, where does the contractor generate the revenue from? So in the whole process, it was thought that we will go for the normal routine biological treatment, etc., etc., etc. And subsequent to that, we will even adopt membrane technology, that is reverse osmosis and other technologies, wherein the quality of water that is produced is such that it can be accepted. It will be accepted by the industry for reuse at their end. But we had another rider there. The rejects that are coming out from the reverse osmosis plant, when mixed with the balance of the sewage, should not exceed the stipulated standards for discharge of treated sewage. So it's a battle. It's a battle means it's a battle which can be won. It is not a battle which is a losing battle. Honestly speaking, it's always a win-win situation. Now, among the biological treatment, you can put on the next slide, or I can just talk impromptu. There's no issue about it. Then after the preliminary treatment, we have that is known as the primary treatment, and primary treatment can be or without be with primary settling. Normally in small treatment plants, we generally go for extended aeration system where we don't go for any settling or generation of primary sludge. End of the day, if the BODs are a bit higher, now how do you select a process? It depends on the capacity, as I said. Extended aeration system is supposed to be quite a reliable system, and for small treatment plants, say up to 10, 20 MLD capacity, extended aeration is reasonably good. However, with extended aeration system, without going in for tertiary treatment or additional treatment, we cannot take care of certain parameters like the nutrients, the phosphates and the nitrogen. The nitrogen can still be handled by putting a denitrification tank and providing nitrification. Phosphorus uptake is not to such degrees that the end phosphates are less than the desirable level. So we have to go for physicochemical treatment for removing of phosphates. So by and large, irrespective of the type of treatment technology we use, to achieve what is required to reuse the water and or to meet the NGT standards which are laid down now, we have to go for tertiary treatment. And secondary treatment mainly involves biological treatment, which could be only aerobic treatment or a combination of aerobic and aerobic treatment, because it is in that sequence. And tertiary treatment would involve physicochemical treatment, that is again some chemical addition, coagulation, flocculation, settling, followed by filtration to reduce the suspended solids concentration. And at the end of the day, in our country, we mainly go for chlorination to take care of the fecal coliform count. Now, the technologies which are being broadly used and are applicable in our country are the extended aeration system, the A2O process. A2O means anaerobic, anoxic, oxic. So the A2O process is is a single unit operation, which is good enough to take care of the nutrients to a reasonable extent. We still need to do something of chemical precipitation to remove the phosphates. Then we have the SBR technology, that is a sequential batch reactor. That is also a very, means you can be rest assured of very good consistent output from that as compared to the other technologies, because the operations are taking place in a batch. But that would also require tertiary treatment to meet the final NGT standards. Then other than that, we have what is known as the membrane bioreactor, which is a misnomer. The membrane doesn't participate in any reaction. The membrane is just used for the solid liquid separation, but that system can sustain a good MLSS concentration, thereby reducing the volume of the aeration tank. So all said and done, the decision that we need to take is dependent on the volume, the characteristics, the space available, the capital cost, the recurring cost, and the reliability of the system. And last but not the least, what is the end use of the treated water? Where do we want to use it? Like if I want to put up an RO plant and reuse the water for high value application, then I should go for an MBR. So this, it's not very difficult, but it is not very easy to really assess what is what. I have given some slides on the ranking and the viability and other things. Now, the next most important, or rather most important thing in my opinion, we have a lot of treatment plants all over the state, country, everywhere. How well are they working? Now, you have to put in a lot of effort or a lot of input to see that the treatment plants that have been put up with a very high capital cost are really operational. And for that, a few suggestions that I have is, number one, flow measurement. You go to the next slide, please.
Sir, sorry to cut you, but if you could wrap up in next 2 to 3 minutes.
Done. I am wrapping up in less than that time. Next. Yeah. Now, back. Continuous measurement of flow at the inlet and outlet. Then very good preliminary treatment is required. Treatment up to tertiary level should be done. There should be online bioassay test. This is a living indicator. If the wastewater or used water that is treated is passed through a tank, which takes up about 10% of the flow is passed through this tank, and certain species are grown, their survival itself is an indication of the degree and extent of treatment. Then in our country, we do another mistake. We design sewage treatment plants for 30 years, which is the life of the sewage treatment plant, and we never get that flow. So it is always desirable to design and build as modular units rather than going for the ultimate capacity right at this stage. And it's just a suggestion. The pumping stations, the STP, along with O&M together should be taken up as one contract or one system. Reason is the pumping station is not working. The STP guy says, what can I do about it? And so on and so forth. So it is basically to avoid all these, redundancy, that it is best that a single entity or a single agency is made responsible or accountable for the whole thing. Now, before I end, I would like to, I have given some references at the end, and I would definitely, anyone is welcome. If they want any specific references or specific books or specific information on whatever I have given in this, I'll be more than happy to share it, either by mail or whichever means. Any questions as and when? Thank you.
Josna, you can take out the... Yeah. Thank you very much, Venkat Garu, for... I know the time is less, but you have done a fantastic job in sort of giving a very basic perspective of what is used water management, what are the typical characteristics, and how do we plan both centralized, decentralized. And we really like that approach of decentralized approaches rather than taking it to one location and then putting it back again for recycling purposes. And also you have outlined different treatment solutions that are available in the market. And as you rightly said, the treatment technology is very much dependent on how much space, what is the value, volume of waste, characteristics of the waste, and very importantly, availability of the power supply and availability of skill sets. These are all the parameters. But I think the treatment plants are doing what every treatment plant does, is to treat. I think the end use application is what you're saying is important. I think these are very, very important. One question before I open up for another 2-3 minutes. Sunanda ji from Swachandra Corporation, she's asking, though I replied in a very practical way, but we would like to have your views. Nowadays, it's fashionable to have inline treatment. Inline treatment is if you put a sort of probes and certain microbial cultures in nalas and drains. We find that is very common nowadays in Ganga Action Plan as well as in a couple of locations. There's not a nature-based solution, but this is like a quick fix solution. So what is your advice to this sort of solutions?
In my opinion, quick fixes are only for quick fixes. They are not long-term. They are just about, something is there and instantly you need to a magic wand. But if you look at the long-term thing, one of the most important thing, why do most of the treatment plants are not working? Because the recurring cost is something which is very difficult for the urban local bodies to pay up. So these quick fix solutions are good, but have a limited application and they're expensive. I for one would not recommend to go for any quick fix solutions unless until it is mandatory at that instance of time.
So tell me something, is it in situ treatment, not in situ, but inline? In a nala, they put some probes and or sometimes they add certain, microbial cultures. Do you think it's a sort of a quick fix for a short-term impact?
Frankly speaking, in my opinion, any quick fix solution has to be a physico-chemical solution. It cannot be a biological system. Just by putting some culture into the nala, which is flowing continuously, and the flow rate is God knows, at what time, how much is the flow.
Yeah,
so you cannot really have a proper control, and any biological system will result into more biological growth. The organic matter can neither be destroyed nor created. So these microorganisms will grow. At the end of the nala, you have to do some separation compulsorily if it is a microbial system. If it is a physico-chemical system, God knows what type of a system it is. It may have some residuals generated, which would need to be removed. Solid liquid separation will have to be done because one form of matter is getting converted into another form of matter.
Yeah. And
so unless until we do an in-depth study and look into the real practical application of the system, it is very difficult to comment about it. But yes, on a no, I am a no for that.
Okay, thank you very much. So I think you made a very important point. We don't have real controls on the flow, especially if you are doing it in a nala treatment. And I'm not talking about nature-based solutions, which we will discuss later. But the ones which Sunandaji is talking about, I think that's very, very difficult to achieve the standards. So I think that's a very powerful message by Mr. Venkat. Are there any other questions from the group, Josna? Otherwise, we will go to the next speaker. We will come back again. Now I invite Mr. Ganges Reddy to share his experience with regard to the nature-based solutions. What is this nature-based solution? Nowadays, everybody speaks about nature-based solutions. And are they really working? How do you make it work? And what precautions we need to take? Can it be done in a small building or it requires huge land value? How does it? Can you clarify some of these issues? And in a very practical sense, do you have real life examples where you have implemented nature-based solutions? Over to you, Mr. Ganges Reddy.
Thank you, Chariji. It's wonderful to see such an audience here, and thanks to
we have a problem with your this.
Everybody
you like to
agree on the basics and advanced. Oh, okay.
Sir, you are on mute.
Sorry, I have a disconnectivity on the internet part.
Yeah, maybe you can off your video and speak. Right now it is better.
Absolutely. So thank you for that introduction. And nature-based solutions have been on the rise, and there's been a lot of interest in the public and also in the officials to adopt nature-based solutions. This nature-based solutions is a push that is not just coming from India. It is actually coming internationally, because we are talking about climate change. Climate change is not tomorrow, it is today. We are seeing the incessant rains and droughts constantly amongst us. So the emissions is coming, from various factors. Today, if you examine, there is ample literature that talks about sewage treatment plants and effluent treatment plants being 6th largest reason for the GHG emissions, which means that every project that we are creating, every problem that we are solving, we are creating a secondary pollution. So there has been a push from the international communities, including World Bank and everybody else, to go towards nature-based solutions that need not create the secondary pollution challenges. So the question, is, are nature-based solutions working? And if they're working, under what circumstances are they working? Is it really a place to adopt such technologies in India? Have we adopted? How is it working? So to go into these details, I would take a quick minute to introduce some concepts that may be covering the ground for us. And then we jump into the core discussion of nature-based solutions. So I represent Blue Drop Enviro. This is the report that says the amount of sewage that we are generating at an average. And this is the amount of sewage that we are able to treat today. In India, we have not even touched 30% of the requirement. This is the case. Out of this, if you have set up thousands of plants, as CPCB went on audit, this is the published report from CPCB that out of 1,200 site visits, 10% are defunct totally, they don't exist. And rest of them, 77% are non-compliant. It is a known fact that STPs are being set up everywhere using different technologies, but unfortunately the fate of these systems is that they are not delivering results. Reasons may be very many, but enough to say that 77% are non-compliant, up to 80% systems are not really delivering it. These are the kind of known conventional systems that we have set up over the years, whether 1 MLD or a 10 MLD or a 50 MLD or 100 KLD. Imagine the kind of efforts that do take. When you just look at these images, the number of moving parts and steel and concrete facilities that go through wear and tear and cause enough challenges. Constant repairs and maintenance, skilled workforce requirement, high energy bills, sludge handling, your ordersomness in the systems, noise in the systems, and finally you spend a lifetime around it, spending money, putting resources behind it. What is the effective life? Can they work? You build a building. Typically, when you ask how long this building should last, people say 100 years or maybe 50 years. And your infrastructure that goes along with these facilities or colonies or buildings has to last along with it 50, 100 years. But I haven't seen any sewage treatment system working for 20 years. And very rarely you find something. Many systems do defunct within 5 to 10 years of lifespan. It's not that technologies are wrong, but the challenges are way many. So if you have to build smart towns and smart solutions, there's been a recommendation coming that we look at nature-based solutions. And we have been building nature-based solutions in India since 2014. We have built a little more than 70 systems in India, out of which about 50 systems were completely passive systems where we have not used any kind of energy. But the challenge has been very obvious that nature-based solutions do require a lot of space. And you don't have space in India as much. So obviously we found it to be very challenging to propagate a nature-based solution which is very effective. So we had to look for alternatives, and we learned that in the Western world has moved forward, integrating nature-based solutions with an advanced aeration techniques that we have adopted in India since 2019. Now we have built more than 20 systems using aerated wetland systems, which is based on force-fed aeration. And these systems have been delivering great results in many, many European countries and within the US, and also in Australian and the Middle Eastern continent also. These systems are less complex, they take low energy, they're fairly sludge-free, they tackle variable loads very smoothly, and they have superior lifespan. How do they look? These are the systems. Some of them are 1.2 MLD here, one is a 2.4 MLD here, is a 150 KLD here, is a 30 KLD here, one built for Honda motorcycles and scooters, one for a mega township, another for urban apartments. You can see this. This is how the systems look. They're quite complex, but the complexity is in the design, not in the operations, contrary to the conventional systems. How do they work? This is how it is. Each of these aquatic plants carry certain type of root system, and each of these root carries certain type of microbial colonies. So if you have a dozen different varieties of plants, aquatic plants, they have different kinds of bacteria that they actually are attached at the root system. And these bacteria actually convert the waste that is coming into the wetland basin as a food for the plant. There is a symbiotic association between the bacteria and the plant, where the fecal matter, organic load, food and all that gets converted, uptaken by the plants as nutrients for their growth. What we don't want, what we don't need is a food for these plants. So this is the nature-based solution where nature has this technology amply available. Unfortunately, the passive wetland systems do not offer the edge that aerated wetland system do, because there is a radial oxygen transfer loss, what is called ROL, that happens at the root system, that the microbes themselves start to take oxygen that is released by the roots. So we have seen that a nature-based solution without aid of aeration requires larger space. When you're able to provide these aeration techniques, it can actually provide the same amount of treatment in a much lesser area. And it also provides for the most latest norms that are being demanded by NGT, the ammonical nitrates and the total nitrogen removal, which were not the case 5 years before. So these aerated wetland systems is what we have been building across the country since 3 years. How does the scheme look like? The wastewater is collected into a wet well, then it gets pumped into a holding tank where we have typically a 24-hour retention. This retention can also be modified and reduced if you deploy some level of energy, but we chose to not do it. And we take this, the water flows by gravity into the first aerated wetland basin and a second aerated wetland basin, and it goes into treated water tank. This is the scheme of aerated wetland system. Passive wetland system will also look the same way, just that the sizes of the wetland basins will change, the depth of the system changes. Everything is calculated quite scientifically based on the incoming load and outlet to water purpose. So we deploy disinfection systems. For a closed loop system, we recommend ozonation. For gardening and all that, typically we don't need much disinfection. We do 1 ppm chlorination. When a water released out of MBBR system or SBR system, when you measure the E. coli versus the water coming out of a wetland system, the E. coli percentage is far less, because there is a predatory mechanism that lies within the wetlands that takes over one species, take over the other. So a lot of pathogens are in the process killed. So your E. coli content is very less, which means to say that the nature has the power to put a tab on the pathogens in the system itself. So it's very effective when it comes to such. This is 1.2 MLD that we built for Deccan Cements. It has a 400 KLD of sewage coming in from the colony and about 800 KLD of their wastewater coming from their blowdown, etc., etc. So the quality of the wastewater is what it is, but I'll show you the treated water quality. This is the treated water quality. This is the quality of the water. And typically, if you want to compare, there are very advanced, sophisticated, good-looking mechanical systems that are coming to the place. If you look at MBR systems, some of them will look like 5-star hotels. They are very well done recently. But by and large, when you deploy SBR, MBBR systems, and when you compare that with the nature-based solutions, I'll show you.
Sir, request you to please wrap up in the next 2 to 3 minutes, please.
Sure. So that's and these are nature-based solution. It's an aerated wetland system. That's the ozonator, the two tiny blowers there. So the mechanization we have is very minimal. The energy cost is barely 20% of a conventional system. We run the blowers only for 8 hours. There are timed blowers, they run on their own. So when we use ozonation, if you have to do for flushing, but for gardening, you don't need that. So where can you apply these systems? Lakes and water bodies, you can do municipal wastewater treatment, you can deploy them in townships and colonies, you can use them for hospitals and schools. They're low on-them cost, 50% of conventional system. They're reasonably sludge-free and they're simple to operate. There's no odor, no noise around these places. They're low energy cost. When I say sludge-free, there is no accumulation that happens in the wetland very quickly. Usually we design our wetland basins to last for 25 to 30 years. There will be slight accumulation in the holding tank. That also majorly you see silt and indigestible grit that deposits in the first 2 chambers. Once in 2 years, you may call a super sucker, remove this indigestible sludge, but otherwise we don't find much deposits there. We also dose certain kind of bacteria into this holding tank. We typically extract the bacteria that is available at the root system. We convert them, we actually dose them ahead of time because we have reduced the footprint significantly to meet the space challenges that we have in urban areas today. The video I've shown you, it's a 150 KLD system built in the backyard of an apartment with about 3.5 meter width and about 40 meter length, 43 meter length. So within about 140 square meters, we built a 150 cubic meter capacity treatment system. And we are building now multi-MLD systems using this aerated wetland. This technology has enabled us that we can treat systems up to 10 MLD comfortably without having to really run around, and systems look as the other one. And you can design them in any forms and shapes. You can really create designs that please your eyes. They can integrate with your landscapes. So our nature-based solutions are the need of the day, that we need to save the planet from emissions. We need to deploy systems that don't take much power. Even better if you don't take any power. But no power means we have to substitute that with alternatives. We have to reduce the emissions. These wetlands are carbon sinks. They actually sequester the carbon. They enhance the biodiversity. Directly, they actually are doing the ecosystem restoration. So these are some of the plans that we have built. We have done about 70 projects. I'm just showing you a bunch of them. We are starting to do in urban areas, rural areas. We are working around lakes and water bodies. I mean, we have done some projects for dairy industry where the BOD levels are 1,000, COD levels are 3,000. We have done for a food industry where the loads are similar, about 1,200 BOD, 3,000, 4,000 COD. I mean, it takes a good deal of design and experience in putting system together. It's not that, you dig a hole and put gravel and put plants, it will work. It's not about knowing what plants will work. It's not that. These are engineered systems. I have seen so many passive wetland systems that got choked and they are dysfunctional across the country that were built in the last 10 years. So the science is pretty matured and it has design principles. If people know how to design the systems, they would last for that many years that they are designed for. We design systems that would last for 30 years. That's the life cycle that we consider as a minimum.
Mr. Reddy, we have a lot of questions. So if you can just wrap up on the cost, you can quickly indicate.
Absolutely. So these are the cost parameters. Energy cost is 24 lakhs versus 7 lakhs, 20 lakhs versus 5 lakhs, and operating space 7 versus 2. We have some bacteria cost here. So in spite of all that, we are 55% cheaper than a conventional system. For a typical 100 KLD system, if you look at the energy cost 60,000, the manpower cost 40,000, it's about 1,11,000. I have not included the sludge cost here. So you're talking about this range of expense for a 100 KLD system, 13 lakhs per annum. And if you extrapolate this 6% cost every year, if it works for 15 years, which is a magic, it doesn't work like that. So you're talking about a 50-60 lakh capital cost is leading to a 3 crore operation maintenance cost. So STPs are not capital intensive systems. STPs are O&M intensive system. You put X on the capital cost, you have to be ready to put 5 to 10X on the operation maintenance cost based on the lifetime that you want to run. So these are the different systems. Sorry, sir.
Yeah. So thank you very much. I think it's a very exciting theme. So I think there are a lot of questions. So I think before I invite Mr. Srikar, the couple of questions which we will take and then we move on. Sudhaji is asking, can this wetland systems be introduced, particularly what you have aerated wetlands, in a bit of hospital environments where the wastewaters are a little different, slightly different? So any quick response to that? Very quick.
Absolutely, 100%. They are 100% apt systems for hospital wastewaters. Actually, a research has been conducted by MNIT Jaipur. They have published results also. Outstanding results on the ABR. So typically when you talk about wastewater, what is there in the hospital wastewater? Again, you're talking about blood, you're talking about sputum. Everything is broken down into water chemistry, it's a protein or whatever it is. So if SBR, MBBR can treat it, the wetland systems are 10 times more effective when it comes to handling pathogens and ABR.
So one other question was about, what sort of species of plants are required? Plants like Canna species, Papyrus species, they were good. So what do you recommend? Is it localized or any species of?
I mean, generally Indian climate, we haven't seen a great change in the efficiencies when we deploy systems. Cypress species are very good. Canna is more for polishing. You can take Thalia delbeta, Heliconia. You can take Typha based on the TDS levels. You can take some reeds, Arandodonax. There are 21, 22 different species that we use based on the inlet characteristics that we have found in the wastewaters. And certain regions, Gangetic regions, you get more Arandodonax and certain species that they do very, very well. Canna, I have seen it doing reasonably okay across the country wherever you are deployed systems.
So there are quite a few 4 questions. I would encourage you to please use the chat box and please respond to them, because one question was about land requirement for aerated wetland system versus traditional wetland. So there are 4 or 5 questions. If you could quickly respond to them in the chat box, then we can save a bit of time. So friends, we saw how wetland systems can also contribute to the treatment of the used water at different levels. Now, sometimes we need, we have land constraints, even in urban areas. We have serious challenges in terms of land. It further, we may need to package it. We may need to keep it below the ground because land is one of the major factors in urban areas. So we have with us Mr. Srikar. So over to you, Mr. Srikar. If you could just take us through the Jocasso system that you really benefits, what are the use cases, and what is the size to which you can scale up?
Yes, I hope you can see my screen.
I'm not here.
Just 1 second.
I can see.
Yeah, now we can see.
Okay.
Go ahead.
So basically some of the sewage treatment plants we have been conventionally using for doing decentralized systems are MBBR, SBR, MBR, and to a certain extent ASP systems. So as Mr. Venkat Puranam said, there are a few issues with the systems when it comes to implementing large-scale systems, especially in building complexes and things like this. The issues that happen are basically with operation, requirement of skilled labor, cost for running the plant in terms of electricity, and also manpower. So I've put down some of the process flow diagrams of how the system is run, but we will skip those in the interest of time. We will just move ahead through the 3 systems through Jocasso. Right there, you can see in the MBR system right here. The MBR model actually does nothing for the biological process. It is in the pre-aeration system, and the MBR just acts like a filter. Yeah. Going to the package solution, it's called a Jocasso system. The system itself is designed from Japan, and it's a patented system by the Japanese government. And there are a few manufacturers who produce this system. The intent from the Japanese government for designing this system was to produce a unit that can be connected to between small households also and larger larger communities, so that the water they're releasing to the closest drain is also treated. So this system goes from 3 KLD at a minimum, which is approximately the usage for 3 households or 4 households, and goes up to 50 KLD. So as is, the system comes in a capsule. It can be a plug-and-play system where only the blowers have to be connected to a main, and the inlet and the outlet can be directly connected to the existing sewer line. Just that we have to find the space, and if there's no space, it is possible to put it above ground also. So inside, the essential process is that the water comes into the separation chamber, as you can see here. It is first allowed to settle, so some of the grit settles. This chamber itself acts as a tiny bar screen. There are bars inside it. After the settling, the overflow water goes into an anaerobic chamber. So this is where there is some media for anaerobic contact and anaerobic bacteria to be sustained. And here it passes through the anaerobic chamber and it overflows into an aeration chamber. The aeration chamber is very similar to an MBBR chamber. There is MBBR media put in it, so there's a little more surface for bacteria to grow and biological actions to happen. After this, the water overflows into something called a sedimentation tank. So this acts as a secondary sedimentation tank in this technology. After secondary sedimentation, you will see something that was very interesting when I saw this plant for the first time. Was in this small plant, they used an airlift pump here to recirculate water. Typically what happens is in sewage or grey water, you will see that nitrate is not in the form of free nitrate. It's in the form of ammonia. Ammonia has to be aerated to be converted into nitrates or nitrites, which is NO2 or NO3. And then it has to be denitrified. And denitrification only happens when there is less oxygen or lack of oxygen. So that is essentially why we recirculate. So similar to what Mr. Venkatpuram was talking about with an anoxic tank for denitrification, that is essentially what happens with this process. So the outlet water, other than the recirculated water, the rest of the water slowly goes up, goes through a disinfection chamber, and the outlet comes into a collection tank or to a stormwater tank. In Japan, most of this water goes through an irrigation channel for if they have plants or something like that, or they send it to a stormwater drain and they grow fishes in it. It was very interesting when I visited Japan, because if somebody is not operating and not maintaining, the fishes in the channel will die, and the authorities who are monitoring will know that there is something wrong with one of the systems connected to that particular channel. So this is a small site where in NTPC Nagpur, where the unit itself is divided into several locations, and each unit is separated in different places. There is a BHEL office, there is a separate control room, there is NTPC itself, there's an industrial canteen, there is a separate power plant, there's also accommodation, there is a small substation in the area. So what happened was, initially they didn't have an issue with regulating the STPs. They had septic tanks and people were coming and collecting the water as and when the septic tanks got full. But when they decided to go for a system, the issue they had was either they lay a septic connection, a sewerage connection throughout the plant, or they go for some sort of decentralized solution, where Jocaso was a perfect fit for it. And this was executed in 2019. So in this plant, which is about 20 by 20, 2.5 kilometers by 2.5 kilometers, you will see 1, 2, 3, 4, 5, 6 plants set up. So the reason for this is because of the variability in size and the variability in consumption that is coming from different units. They needed a system which could vary in process design and how much capacity, process design relatively remains the same, how much capacity it can treat, and based on the space where it can fit. It can be installed in multiple orientations. So I will show you a few orientations we have installed there. So these are essentially above ground orientations. The one you see on the right is the biggest plant, which is a 300 KLD plant, which is set up in 6 units of 50 KLD. On the left, the plant is a much smaller plant. It's a 120 KLD plant. So what essentially is done is there is a septic tank constructed on the bottom, which is already existing. We have taken pumps taken it to a divider box, which is essentially V notch to equally divide the flow rates. And the water from that goes through the Jocasta system and it is taken to a treated water tank, which is just connected below it. So this is the central picture on the bottom. This is in a hospital. So in the hospital, they had free area. Earlier, there was no connection required. When the new NGT norm was done, they needed a new connection and there was no other free space. So there is a septic tank just behind it. If you see below the building, you'll find a small tank here. This is a septic tank. So the water from there comes to this plant and the overflow goes back to the drain. These are some above ground installations. Some of the areas we find that in building complexes, most government offices, small areas like Zilla Parishad schools, small parks, there is no space to accommodate these above ground. So it can be done in a below ground model also. So these are some of the below ground models. So this system essentially is integrated into the ramp. So what has happened is this is a driveway. And what they've done, they've excavated this, essentially constructed civil columns and beams, cast a slab over it after inserting the Jocasta system, and they've plugged it. So all the maintenance that has to happen happens through the manholes. And the only maintenance that is to be done is filling the chlorine chamber. And once this sediment gets full, you use a super vac or something like that, put a vacuum tube through the manholes and take out the sludge. So for that, because we could have done it that way, here it was put in a driveway for compliance, but essentially they're very happy with the system and they're reusing some of the, here you can, okay, sorry, I'm going to cut. So this is one of the sites where the plant is essentially put underground. So this is in the garden. So for this system, this is directly connected to the sewer line that comes, and this outlet is directly diverted to the stormwater drain. So in this case, we don't need to operate anything. There is no treatment to be done. So there are two blowers, which is here, the white units. They generate, the system is in fact very beautiful. They generate noise of 60 decibels, which is less than what I'm talking in right now. And the only flue gases generated come out through this CPVC line. Essentially, there is no smell. This is the front of their office building. So you can see the main gate here. This is the front of their office building. And this kind of systems can also be done. So in certain sites, we have done systems where they're not completely put under the ground. There is a bund built around it and the system is put above ground here. So that is because of the invert level. Based on the invert level, we didn't want to use any pumps. So we decided to put the system a little above ground. So these kind of orientations can be done. Obviously, there are some advantages to this kind of design. So you don't need new pipelines or new septic tankers to carry away septage and grey water. That is, if there's relatively a new community which is coming back to setting up a new system, this can be a good solution. Manpower requirement is almost non-existent. The only thing that has to be done is a chlorine tablet has to be filled once in 4 to 6 days. And the bar screen has to be cleaned once in 4 to 6 days. And it's a very, very low manpower cost. In fact, one of the big advantages we have is when we place these in some of the smaller apartment complexes or some of the smaller hospitals, is that we tell them we can train a security guard, and if you pay them like maybe a little more, they will do the work, and you don't need to have a dedicated man. So I myself have a lot of conventional systems we've executed and we are maintaining in and around Hyderabad. Some of the biggest systems in Hyderabad, we're maintaining them. But the issue with that is the site we're maintaining, if it's close to 1 MLD, the cost implication on each person who lives there, each stakeholder, is almost non-existent. But if it's a 50 KLD plant, in fact, I remember discussing with Venkat Puranam sir a few months ago. But if it's a 50 KLD plant, the cost implementation is so huge that people choose not to run them. So that can completely be avoided by using a system like this. Safe disposal of sludge. Yes, you can use a tanker and that can be taken to an FSTP. And we are implementing FSTPs in multiple ULBs. So that government initiative can be completely utilized using these plants. Low orders and noise levels, especially because the noise level that is normally generated is less than 70 decibels in most cases. And normally that is less than road noise, that is less than ambient noise in and around where we stay. Reduce power consumption. There is no pumps we need to use. As long as there's an inline connection, the system itself is very simple, runs by itself. It's run with an airlift pump. So that helps with not using a power connection. Thank you for your time.
Thanks, Shrikar. This is fantastic. So I think I will give the context a bit later, but just one or two questions. What is the typical size of a 50 KLD unit looks like, in terms of area? What is the area requirement?
A 50 KLD unit normally is around 3 meters wide and goes around, I'd like to say around 26 meters in length, okay, including all the connections, including the internal pipe.
So, Mr. Dongo, I think that answers your question. So, just to give a bit of, you heard about, before I invite the next speaker, you heard about different solutions, nature-based solutions. We have heard about package treatment systems, and Mr. Venkat also given an overview on various, how to plan as well as what sort of technologies. So one of the important things that we can learn from this, from a citywide inclusive sanitation point of view, particularly dealing with used water management, grey water management, as we say, because the black water is dealt by the septic tanks or fecal sludge treatment plants are sort of sorting out that bit of wastewater. The critical aspect is the regulation. If you want package treatments to come and solve the problem of individual pollution generator, you need to have a regulation from at the building approval level. Suppose I'm constructing a gated community, if I'm constructing a ground plus 3 structure, 20 apartment structure, then like in Japan, every house, even if it is a 5-member family house, they have to go for Jokaso system, but we don't have those regulations. So if you want an advanced treatment, you need to also have advanced regulations. So we need to think about it, number one. It means we need to have building code, town planning rules. We need to have some of those provisions built in. Otherwise, we end up with grey water going into nalas and drains and polluting the water bodies, and also creating mosquito breeding, because the solid waste is also being dumped in these nalas and drains. The flow is not very efficient. So that's how the disease burden increases in the community. So we need to understand, while we have regulation for having a septic tank or on-site system, we don't have a real good regulations in terms of the building level or at a community level for this grey water or sewage treatment also. So this is number one. So the practitioners have to start looking at it. Second is, even if there are regulations, the decentralized approach, what Mr. Reddy mentioned, he used what is that, 3 feet or 3 feet or 3 meters or 3 feet width along the building, and he converted that into a very nice treatment along the way as through the wetland system. So it means that there are solutions available. It requires certain design thinking to solve the problem at a household level, at a community level, and sometimes at a, I would say, at a regional level, because we also need regional units. What Mr. Venkat mentioned, we may need certain big plants, 10 MLD, 5 MLD, 15 MLD, based on the size of the city. But I think it makes much sense to solve where it falls, where it gets generated. And that's the key message coming out. Are there any 1 or 2 questions before we invite the next speaker? Anybody would like to comment? Anybody would like to ask questions? Yeah. So economy of scale plays a very important role, especially in terms of, absolutely right, Mr. Venkat, I think economy of scale is very important. However, if you bring in good regulations and good market play, the size of the unit as well as the cost could come down. And then I think it would force the technology to go for decentralized systems. I agree that the larger economy of scale projects are maybe better, cheaper in certain situations. So rather than PCB, bioindicators are the best to state the functioning. Absolutely right. So that's where yeah, go ahead.
We have done this, sir. In one of the plants, what we've done is they need water for cooling tower, and they are going to use it. They're going to take it into a clean room. So what we had to do, there's a pipe running through a clean room. So what we had to do is, after the SBR system, we put an ultrafiltration system. In the outlet, we put a fish tank.
Okay.
If the fish are alive, it is clean water.
Absolutely. Now, this is a very interesting thing. You know, I have seen a couple of sophisticated systems, including in Israel. The water treatment, the best test that they do after all the treatment, they have bioindicators, exactly what you said, very sensitive fish. And then only they put the water into the pipe system for drinking applications. This I'm talking not the wastewater, but the water, even for water treatment. So absolutely right. Bioindicators are quite efficient in testing and it's also real time. If it is a normal system, by the time we take sample and measure, I mean, there is a delay, whereas bioindicators can work much quicker than probably, and of course, Dr. Banerjee is an expert in that, so he should be commenting on this, but never mind. Are there any other questions? Otherwise, Josna, we can invite Mr. Dorai to take Mr. Dorai Naraswamy to take the next session, which is very, very important, is a co-treatment. So can it be made locally? What is this? Can it be made locally? Jocasso. Can we use Jocasso as a FSTP where tracks will convey sludge into? Okay.
Yeah, I like to answer that.
Yeah, please go ahead.
Jocasso as is used for treatment of water or used water or gray or black water. Not really in terms of sludge. So what happens is in an FSTP, there is a Jocasso design where after dewatering of the sludge through a belt press or a filter press or something like that, the water that comes out of it can be treated through a Jocasso unit to reach PCB limits. So that can be done. We can pass it through a belt press, get cake out of the sludge, and the water that comes out, we can treat it to PCB standards. Sorry, NGT standards.
I'm happy to inform you that when you visit Hyderabad, you would see FSTPs using Jocasso system. After the liquid-solid separation, the liquid will go through the Jocasso system and the solid is treated separately. So these are actually implemented. Your question is absolutely valid. Jocassos can be used for liquid treatment, but I cannot put the septage directly into the Jocasso system. It's not designed for that right now. Are there any other questions?
No, I'm really sorry to cut this conversation, but we have the speaker waiting.
Okay, please go ahead.
I invite Mr. Dorai Narayana to take up the session. We have given a brief introduction of you, sir, prior to the session, so I'll hand it over to you.
Welcome, sir. Sorry to keep you waiting.
Hello, sir. How are you?
I'm fine, thank you.
Yeah, welcome. I want to appreciate this opportunity to speak to all of you. I see there's a huge number, more than 70 people here, so that's really good. But I've been told that most of you have actually seen the presentation, the recording of it, and so I will not go into very detail, and hopefully there's more of discussion that will come out of here. So I hope you all can hear me well, and I'm not speaking too fast or slow or whatever. Okay, so we are going to talk about co-treatment, and this is co-treatment of septage of fecal sludge with sewage, not with solid waste or anything like that, only the septage fecal sludge co-treatment with sewage. And broadly, the topics will just touch on understanding what is this co-treatment about, the opportunities that present themselves in our cities, and the limitations and adaptations that we have to understand, right? So the first thing to understand is that septage and fecal sludge are different from sewage. There was a question just now about Jocasso, whether it can be used. When you do a solid liquid separation, then the liquid part of fecal sludge is closer to sewage. Then it may be possible to treat it in a Jocasso or in a sewage treatment plant. That's what we are talking about. So this co-treatment we talk about is basically the liquid part of the septage of the fecal sludge. So one thing to understand is the volume differences between fecal sludge or septage and sewage. I think you all may know that the volume of sewage from an equivalent population, in this particular case, we are taking an example where the city has got about 50% sewered and 50% non-sewered. The volume of sewage is about 100 times or even more compared to the volume of septage that is produced by the same number of population in the city, assuming, of course, regular desludging and things like that. So the thing to know is that sewage volumes are far higher than septage volumes from equivalent population. Second thing to see is that there is a variation in flow. Sewage flow, you know that there are two daily peaks, morning and evening, caused due to the pattern of water usage in the premises. So people use more water in the morning and sewage is generated more in the morning and then again in the evening. But for the case of fecal sludge or septage, the variation depends on the truck volumes, the frequency of the truck arriving at your treatment facility. So it's pretty much dependent on when one truck arrives, you see one small bar there. Sorry, let me just get a pointer if I can. Yeah, so you can see these are the small bars and you can see they are relatively small compared to this. And they also like when a truck arrives, it discharges, right? Whereas this is continuous like this. Now, what happens when you combine this in a co-treatment situation where the sewage is continuously coming into your STP and you then bring in trucks? One more point to note here is that these trucks only arrive during working hours. They could be 9 to 5 kind of a thing. So the remaining part of the day or the night, there is no flow of septage. So the septage flow comes in only during this time. Now, what is the impact on that? This is a sewage flow pattern that we saw earlier in this slide. Similar thing on a larger scale. If we superimpose the sludge flow here, you see it's negligible. The difference here is negligible. So what we're trying to say is that in terms of volume, adding of septage usually does not make a difference, right? So the flow itself is not the consideration. A lot of times we say we are going to add 1% of septage and so on, but it is not really the flow that matters, but more of something else, which we will see. So we are going to now look at this concept of concentration and loading. So we are used to saying BOD in terms of loading, in terms of concentration, that is either ppm part per million or milligrams per liter. But in the designing of the co-treatment, what is more important is the loading. And the loading is obtained by flow multiplied by concentration. So if you have a flow here, for example, this is the flow from 100,000 population, 1 lakh, yeah, 1 lakh population sewage, and equivalent 1 lakh population septage, 56 meter cube. You can see it's far smaller. Now let's look at the concentration of suspended solids. Sewage typically about 300 milligram per liter, and I'm going to just take a assumed figure of 7,000 milligram per liter for septage. So here, the volume here of sewage is very much higher than the volume of septage, whereas the concentration of suspended solids is very much higher in septage compared to sewage. But when you want to talk about the impact, you must then look at the loading, which is multiplying this times this, and that's what you get. So you find now you get 3,240 kilograms of suspended solids from the sewage, and for the same population, 392. Hope I can see that. Yeah, 392 kilograms. Now you are able to compare and say that the suspended solids contribution from the septage is about slightly over 10% of this, even though the volume is very, very small. So we, in our designing of co-treatment systems, this is our main thing that we must consider, this the loading rather than concentrations. Yeah, I hope that's understood. And for BOD and nitrogen and whatnot, COD, everything, similar ratios will apply. You multiply the flow times the concentration to get the loading. And that's the thing that you will look at. Now let's look at the variation of flow over the day. In this case, this is variation of suspended solids over the day, right? And this is kilograms per hour, right? Just now what we saw was the total over the day. And here we are looking at instantaneous thing per hour, yeah? This is the variation. And it follows the variation of the sewage flow, because when the flow is more, there's no more suspended solid coming in, right? Plus flow multiplied by concentration. And here, when you add the concentration of suspended solids contributed by the septage, this is what happens. For this period, of the day when the tankers are coming in and discharging, there is a substantial increase in the kilograms of suspended solids per hour at any time for each hour. Here, there's no difference because there's no septage being brought in, and here too. Whereas during this period, there is quite a bit of difference here, right? So even though over the day it's not that much, the flow is not that great, and the concentration over the day is also not much, but an hourly distribution, it can be different. And this is so for BOD as well as nitrogen and water also. So what happens is that many treatment systems have long retention times or process times. And therefore, this gets evened out over the process time. Let's say your activated sludge, 18 hours, 15 hours, it gets evened out. But if you have a process which is a very short duration, say it falls within this duration, the impact could be very great because the entire duration, the suspended solids that it's designed for is being exceeded by maybe 15 to 20%, right? So we need to be cautious about that. Now let's look at the organics part. It's another very important thing that when we talk about septage or fecal sludge, there are two types. One is digested septage, another is fresh septage. What does it mean? Digested septage has remained inside your containment for a substantial period of time and has already undergone some level of stabilization. Whereas fresh septage is being dislodged from the containments on a more frequent basis. Maybe it's a communal septic tank, it could be a community septic tank, it could be a public toilet septic tank, and then it's called fresh. What's the difference? In the digested septage, there's a very high percentage of non-biodegradable and particulate matter. So this part, which is about slightly more than half, I'm just taking an indicative figure, yeah? So what happens is that this more than 50% cannot be treated in a biological system because it's non-biodegradable, right? So you need to remove this thing. How do you remove it? Through a solid-liquid separation. Because it's particulate, this will separate out in a solid-liquid separation. And you are left with only the remaining part that you have to co-treat in your treatment facility. Whereas when you have a fresh thing, you cannot do that because the readily biodegradable and slowly biodegradable part constitutes about 90%, and only a small part is particulate and non-biodegradable, which means you need to do something about this first before you co-treat. So now this is indicating to us that depending on what type of sludge you're bringing in, is it digested sludge coming from pits or septic tanks which are being dislodged on a few years basis, or it's coming from fresh sludge, which is coming from septic tanks or containments which are being emptied very frequently. Then for this type of cases, you may want to deal with it slightly differently from this kind of cases, right? And let's see what we do. So this is a full pie chart. So when we look at options now, so you have a city. Does the city have a sewage system already, or is it being planned? If so, if no, then of course, there is no opportunity to co-treat there. But you might have some neighboring cities where you can send the sludge to and cluster it there, yeah? Or you need to just put a fecal sludge treatment plant, standalone dedicated one. If yes, then if it's a new STP being planned, you can evaluate the logistics, which means how far is that new STP from where the sludge is being generated, because your sludge is going to be transported by tanker. So look at that sludge and then just design this new STP to co-treat. Relatively easy and straightforward, right? But if you have an existing STP, then again you have to evaluate the logistics and then look at available spare capacity. If the STP is already almost fully loaded or expected to be fully loaded in the next few years, co-treatment is not an option. If not, then you can start looking at what are the technical constraints that exist in this particular STP. And do you need to do something like pre-treatment of your sludge or some modification or retrofit of the STP before you co-treat? This is broadly the kind of flowchart that you would go through. And these are not mutually exclusive things. And there could be options where all three could be done in STP. Part of the septage could go to new STP, part in existing STP, and part in standalone STP. So it could be a combination of these. So when you have a dedicated STP, these are the options. If you have either a dedicated STP or co-treatment or a combination, it can mean interim co-treatment, whereas a permanent arrangement is for an FSTP, or it could be the co-treatment itself is permanent, which means you intend to keep it for good. Yeah, logistics are important, and the remote addition of sludge at what we call pumping stations or manholes, we need to be very cautious and need a proper decanting facility where you have some kind of screening and maybe some solid liquid separation. Some people monitoring that so that illegal things are not being discharged and abused and causing a problem to your sewage system. So logistic problem can be overcome by these decanting facilities, provided they are designed well. So the crude addition, what I call crude addition, is really when you just take your raw septage coming from the tankers and just add it into your inlet of your STP. So this I would advise very, very strong caution that not to do this unless you are very sure that it's a very, very small quantity and unlikely to affect your STP. It is much better to do it after some kind of a pre-treatment, or even if it is already very dry, you can do a direct dewatering. Right? So the influencing factors are the availability of the STP, the size, the capacity and suitability, the logistics, where it's located, the relative volume of what is the sewage flow coming in compared to the septage flow, the nature of the sludge, and cost, of course. What is it better to have a separate FSTP or to co-treat with some modification? Right? So when you have fresh sludge, we saw what was that, right? So the first step before you co-treat is a biodigestion. So you should have a upfront digester to stabilize the sludge before you go in for co-treatment. Whereas if you have septage that is coming from septic tanks, leach pits, and so on, where it is low biodegradability, but mainly particulate, then a solid liquid separation is advised upfront before you co-treat the liquid portion of it, right? And the solid liquid separation will remove quite a bit of the pollutants as well. Yeah. And if it is dry pits, which are not very common in India, but common in places like Africa, where people don't use water for ablution, and they are also water-stressed areas. So these are dry pits where the fecal sludge is well digested with very low water content, and also the proportion of biodegradable matter is low. Then you can actually do a direct dewatering steps. If you have a drying bed, for example, you can apply it directly on them. Yeah. So these are just what it shows. This is a crude one that I should say. You just have the STP and just add in here, right? Without any pre-treatment, without any digestion. Here is a digester that you have upfront for fresh sludge. And add it here, digest, and the sludge, of course, goes to your STP's sludge stream. And the liquid then just flows through together with the sewage. And when you have fresh sludge, these are typical characteristics. And when you do a biodigestion, the BOD is reduced, solids are reduced, and solid liquid separation improves also. And this is where you do a solid liquid separation. Most common, liquid part co-treated, the solid part sent through here. Sorry, anyone asking a question? And you can see here, when you do a solid liquid separation, depending on the type of method you use, the total solid reduction and BOD reduction can be very substantial, right? So you only then left with the remaining part to be co-treated. So that brings it very much closer to a sewage characteristics, right? So this is what I would recommend for most areas where you have stabilized septage coming in. Try to have a solid liquid separation before co-treatment. And this, of course, is a direct bringing in of sludge, adding it directly to your drying bed or whatever in your sludge treatment unit. Okay. Some of the technical limitations you will still face when you do the liquid stream co-treatment is that the process units have some design limitations, right? Or the hydraulics, this is usually not a problem because we are adding very small quantities, so it's not a problem. The solid loading could be a problem. The organic loading could be a problem. oxygen requirement could be a problem. And the options, we can either limit the quantity of septage that we are adding, pre-treat it to bring the sludge characteristics closer. This pre-treatment would include either solid liquid separation or digestion, or you can retrofit your limiting process in your STP, add some process steps, add aerators, for example. So you could do any of these things to retrofit to be able to co-treat. Need to remember that all these things, the sewage flow, the sludge flow, and the characteristics may change over time. So we are not doing a one-off thing, but you have to keep monitoring that what happens in the course of over the period of time that you're doing the co-treatment. Or for the liquid stream itself, these are the possible issues that you might have. Insufficient aeration capacity, lower oxygen transfer rate and uptake, because the amount of solids that are in your reactor is going to be much higher. So the oxygen transfer rate and uptake may also be affected. Right? Lower mixing because of high solid content again in your aeration tanks. Higher solid loading and residence time in the reactor. Higher surface overflow rate of clarifier, considering possible lower settleability of the combined flow. Higher oxygen uptake for nitrification. This is in case you have nitrification, denitrification steps. And unavailability of sufficient organic carbon for denitrification. This is in the anoxic zone of your STP. Right? Again, solid liquid separation will mitigate quite a lot of these issues that you might face in your liquid stream. For new facilities, we can easily design to meet, to co-treat. For existing facilities, these are the things we can do: pre-treat, blend or equalize, reduce volume added. Oh, I forgot to mention this. Earlier we saw that we have fresh and stabilized sludge. Some cities may have a combination of this. So there are options of either blending these or having two separate streams, depending on the relative volumes that you are dealing with. Reduce the volume added, monitor the quality and regulate tanker operators. This is in case of any toxic stuff that is coming through the tankers. Increase solid handling capacity, primarily in your primary settling tank and so on. Oxygen supply can be increased, and tankage capacity is quite difficult to do by adding tanks or increasing tank size, but this is last resort. Yeah. Final words: start small. Whatever analysis you do, don't take chances of fouling up the STP. So start with small quantities and gradually work your way up. Select large STPs. Don't go for co-treatment in small STPs where process control is low, may not be manned, and chances of things going wrong can be very high. Right? So select large STPs with sufficient spare capacity over the planning period, at least for 5 years. Be cautious of end products. If you are using the end product, either the water or the biosolid from the STP for certain purposes, for example, like composting, if you are going to co-treat that sludge that you are bringing in, you may not be in control, and there might be some industrial stuff there, which makes your end product difficult to reuse. Right? Logistics, I mentioned about the remote decanting stations. Planning for co-treatment on a cluster basis is always very good, because when you have an STP in a big city, try to have co-treatment of sludge from adjacent smaller towns. One issue that I face is institutional issues, where if the sewage treatment plant is operated by one entity and the septage management is by another entity, they find difficult to talk to each other. So this may be one issue that you may face. The variability of the sludge is very, very high. No matter what samples you do, you'll find that it varies from place to place, from tankers to tankers, which means that you must do some kind of a checks on incoming septage. For every tanker, you can do some visual tests and some basic tests which are available to ensure that it's within what you have anticipated when you designed it. So these are two links which, of course, you can take it from there later. So this is a book on co-treatment. And these are some worksheets which will help you to do a preliminary planning analysis of whether co-treatment is possible, what quantities can be added, and whether you need to pre-treat before you co-treat. Yeah, so this is going to give you not a design thing, but more of a planning planning tool for you to decide on co-treatment. All right. So I'm going to stop here and just open up for any questions. I see some in the chat already. So shall I take those first?
Sure, sir. Please.
Yeah. So we have centrifuges at most STP. Is it desirable that the septage is dewatered along with the STP sludge and the decanted liquid taken for treatment? So this is something that is debatable. We have a few STPs in Kuala Lumpur in Malaysia where we have co-treatment, but the sludge that is coming from septic tanks is being dewatered separately. It is not being dewatered together. So sometimes it's a matter of looking at the characteristics of the sludge. The STP sludge that is coming out is quite a different character, right? It is very, especially if it's coming from an activated sludge plant, it can be very fluffy and difficult to dewater and may require more polymers or different type of polymers for dewatering purpose. So depending on the quantities, if the quantities are small, you could do it together. But if the quantities are large, it might justify you to have a separate centrifuge or separate some other, even a drying bed, for the sludge that is coming from the septage. Yeah. Can we have a larger holding tank at the STP and feed the fecal sludge during it? Yes, this is possible. This is the equalization thing that you could try, and you can have a holding tank, and it's also good because it sort of blends the fecal sludge or septage that is coming over many tankers. And also gives you a view of, in case you find one tanker is bringing in blue colored sludge, for example, then you stop it before it gets into your STP. It is in the holding tank and you see it's getting blue, something is wrong, right? So there is a kind of a safety step that is also can be used here. Yeah? Total nitrogen might be possible as the total nitrogen in the septage is high and is order of 200. Yes, it is true. So you need to also, if you're removing nutrients, you have to check that after the dewatering, the blended sewage plus septage, what is the total nitrogen? And whether your STP has been designed to handle that or not. If not, you may need to reduce the volume of septage or do some other process modification in your STP. If you look at the model in the worksheets that I shared earlier, it also looks at nitrogen, right? And it will tell you whether there's a risk for nitrogen, risk on BOD, risk on oxygen, or whatever. So it will point out to you which particular aspect of the co-treatment might be a risk where you might want to look more closely, right? It's not as a design thing. It's not going to tell you what to do, but it's going to show you where the problem might arise. Okay, I think those are the questions that are here. So are there any others? Is it clear, or any part that you'd like me to go through again? Maybe it was not clear. Professor Chari?
Yeah, sir. There was a question earlier. Now, if a city official wants to self-design or at least do a bit of detailed planning, your manual and book and also the worksheet, can they help them to empower themselves to design a co-treatment system following the principles outlined in the book and the manual as well as the worksheets given by you? Would you like to throw a bit of light on that?
Yeah, I wouldn't call it a design book, and I wouldn't call it a design
planning tool. It's a planning tool.
Yeah, it's a planning tool. It's a planning tool. So if you are looking at an option of co-treatment in your STP, right? So you can put in the parameters, the design parameters of your STP, the size and the current loading and everything. It's all the worksheet will take all those, and also the characteristics of the fecal sludge that you intend to put, the characteristics of the sewage that you are designed for and you are actually getting. So you can put both, and then you can play around by increasing the amount of fecal sludge to see what is the maximum that can be co-treated at an acceptable level of risk. Right? That's not the end of the story. After that, you may need to do a more detailed process calculations to reconfirm that. And that's when I would say that, yeah, I think we are reasonably confident that I can add a certain X quantity of septage to this STP. And I would start with X divided by 2, maybe 50% of X, and slowly work myself my way up to X. So that would be how a city official could be able to do that. So before he engages a consultant, for example, he might be able to use these worksheets, which a reasonably competent technical person should be able to do. That, yeah, this is an option that is viable and can be considered further. I think that would be the conclusion that comes out of the worksheets. Not a conclusive thing that you go out there and do it, you know. Yeah. I wouldn't advise that.
Yeah. The other thing
is, there are many assumptions. There are many assumptions that have been made in the worksheets. We cannot cater to everything, you see. So there might be other things that a designer would consider.
Sure. So the other one, Josna, can you remove the screen so that we can see the participants?
Shall I stop?
Yes.
Yeah. So just to, for the benefit of everyone, particularly those who are from India, most of you are implementing what is called Amrut as well as other projects. These projects, now SBM also is promoting Swachh Bharat Mission also for small and medium towns. There is a provision for wastewater treatment. So it is in this context, you need to be very, very opportunistic in optimizing the land, optimizing the resources, optimizing your operation and maintenance for going for co-treatment. So wherever there is an opportunity where you are setting up STPs, then follow the design principles outlined by Doren Araswamy, and then use some of the design principles, guide your consultants, those who are preparing the DPRs, you encourage them to go through this document so that they can use these principles and then incorporate in the DPRs that they are preparing for the treatment STPs that you are putting up. This is very, very important so that you need not all the time have a separate FSTP as well as a separate STP. So wherever there is, you think the STP is closer to the city, not too far, because if it is too far away from the city based on the topography and hydrology, then the desludging operators may not travel to that distance. So you need to use your judgment, but wherever it is amenable, you can encourage co-treatment. The design principle shared by Dorai sir actually can be very, very useful for your technical consultants. And I think you can do a good job in optimizing your time and resources and money. So I think beyond that, I don't have any other comment to make. Josna, Dr. Banerjee, over to you.
Can I just add one more thing?
Yes.
When you look at co-treatment and you find that it is possible, one of the advantages is that the operating team can be optimized, because in the same site, you're also co-treating fecal sludge rather than the two sites. So in terms of manpower optimization is much easier to do that, right? So these are many advantages, and the land, and usually to find a fecal sludge treatment site, not so easy because you need to look at adjacent developments and sensitivities of people and so on. But this also now applies when you do co-treatment. So when you have a co-treatment at an STP site, normally an STP site, there is not much of tanker movement in and out, right? Because the sewage is coming through a pipeline. But once you do co-treatment, there's going to be tanker movement. So you must see the sensitivity of the adjacent areas, whether a tanker movement might cause problems for the people in that area. We have had that kind. So one of the considerations when you choose the STP for the co-treatment is that the location of the STP must be such that it is possible to have tanker movement without causing unease to people who are living around there. So in Malaysia, we have many large STPs, and we cannot do co-treatment in many of them because of this factor. There is a sensitivity. Of course, the STP itself has some issues, but those are taken care through odor control and things like that. But when you have a tankers moving in front of your house, that causes a lot of problems for people, and there will be a complaint. So this is something to be considered as well. Yeah. Okay, that's about it. Thank you.
Thank you, sir. Thank you so much. participants. Any other questions from any other participants? If there are not, there aren't any, we would close the session by saying that tomorrow again we join you for a session wherein today we spoke of used water management, we spoke of co-treatment. Tomorrow we'll be speaking of dedicated fecal sludge treatment plants, and we will be having an e-exhibition on the designs and operations of fecal sludge treatment plants, where we'll be talking about electromechanical units, we'll be talking of electrochemical units, we'll be talking of biological units wherein fecal sludge is treated. So we'll have a series of speakers who would be demonstrating, talking about the treatment technologies and the operations and how we do it. So tomorrow again at 4 p.m. we meet you at this same link.
Thank you.